Welcome students. We want to discuss about triple integrals in cylindrical coordinates. Again, the idea is in double integrals we had polar coordinates. Now for triple integral we are looking for something which is analogous to polar coordinates. So what is cylindrical coordinate? Cylindrical coordinates are essentially polar coordinate for x and y and vertical cylindrical z, and this gives you the polar coordinates. To be precise, let's take x equals to r cos theta, y equals to r sine theta, right? This is the polar part. And z will be z, all right? So this is the cylindrical setup. What is the way to go other way around? So suppose if you're given x, y, and z, given x, y, and z, we can go r is given by r square equals to x square plus y square. Theta is, so tan theta is y over x, so tan theta would be y over x. So theta would be tan inverse of y over x, and z remains as z. So this is the vertical z we are talking about. Now again, what is the motivation for cylindrical coordinates? In triple integral, sometimes the region is nice to be integrated in terms of triple coordinates. This is similar situation when you had polar coordinates. Some circular regions were easy to integrate in polar coordinates than doing it in the Cartesian coordinates. Okay, so we'll come to that in a minute. So first of all, let's see some dictionary. So let's take a rectangular coordinates. So find rectangular coordinates of point P having cylindrical coordinates 2, pi by 4, 4. So we have x, y, z is going to be 2 cos pi by 4, 2 sine pi by 4, and 4 remains 4, right? So z is unchanged. So this is the cylindrical coordinates. Sorry, from cylindrical coordinates to polar coordinates, right? So my bad. This is from cylindrical coordinates to Cartesian coordinates, x, y, z coordinate. Okay, so now, well, I mean, of course, you can simplify this to see the number, but this will be 2 by square root of 2, 2 by square root of 2, and 4. Now let's see what is a cylindrical coordinate of this point here. So in this case, we get r equals to x square plus y square square root. So r square is x square plus y square. So square root of minus 1 square plus 1 square, which is square root of 2. Theta is going to be tan inverse of y over x, y coordinate over x. This is going to be tan inverse of 1 over minus 1. So tan inverse of 1 is pi by 4. So this is going to be minus of pi by 4. And well, z is 1. Now the question is, so what kind of regions are nice in the cylindrical coordinate setup, right? So let's work it out with few examples. So we have z equals to x square plus y square. It's a paraboloid. So y square, and if you put r cos theta square plus r sine theta square, take r common, you'll be left with r square times sine square theta plus cos square theta, which is r square. So z equals to, so seems like paraboloids are simple, right? So you get z equals to r square. Yeah. Similarly, how does an equation with cylindrical coordinate r equals to 2 looks like? So r is 2 implies x square plus y square equals to 4. So in the cylindrical coordinate setup, this will look like a cylinder of radius 4. Yeah. Similarly here, z equals to r square will look like, when r is, the z is 0, you get r square. So it looks like, this is what it looks like, right? After all, it's z equals to x squared plus y square. So objects like paraboloids have nice expression in terms of cylindrical coordinate. Objects like x squared plus y square equals to 4. Cylinders themselves have nice expression in terms of cylindrical coordinate. Hence the name cylindrical coordinate, of course. Now, what does this describe the surface whose cylindrical coordinate is theta equals to pi by 4? So again, you have x, y, z, and theta equals to pi by 4 means theta equals to pi by 4. So this angle is pi by 4, and so this is a plane of theta equals to pi by 4. All right. So these are the regions which look nice in cylindrical coordinates. You will soon see that each of this is also called a cylinder. Okay. We'll see that in a moment. So now again, so idea would be to integrate. So we want to integrate. We want to find out triple integral of f of x, y, z dv, where dv is a volume element. Now the way the volume element changes is, so initially you had v equals to dx, dy, dz, right? And this can be changed as r, dr, d theta, right? If you consider this as in 2D, right? So if we look at it as 2D polar, you get r, dr, d theta, and then you have dz. So this is how the volume element looks like in the cylindrical coordinates. So notice that we are approximating our volume by pieces of cylinder like this, right? So area of this sector we have already seen is r, dr, d theta, and this is dz. So when you multiply it out, you get the whole volume element. So in cylindrical coordinates, the triple integral transforms to, instead of x, we have r cos theta. Instead of y, we have r sine theta. Instead of z, we have z. And then we have r dz, dr, d theta in some order, depending on how you choose u, right? So u is representation of limits on z and r and theta, appropriate to describe the region E over which you are integrating. Right? So I have to change it to u because they will describe the same region, but in different, the bounds will be different for r, sorry, r, theta, and z. So again, how do we go about it? Well, there are 4 important questions we should answer, like we did in the triple coordinate. So recall in triple coordinates, we did 3 things for the geometry. Namely, we understood the footprint, we understood what was the top and bottom surface for the integration, we understood what were the sides, and then we had, once we had the footprint, we had an integration plan for the footprint. Now let's make this whole process concrete with examples. So let's start with, before I go further, I think there is some merit in discussing how do footprints look like. So footprints look like the following. So if you do R first, then the footprint will be in theta z plane. So in that case, so theta z, so theta is basically the angle, right? So for certain angle, you will get, this will be your footprint region D, in case you have what? Theta z footprint. All right. Again, I'm assuming that D is a rectangle, that the footprint itself is a rectangle. All right. That need not happen all the time, but okay. Now, next one is R theta footprint. So R theta footprint is similar to what you had in polar coordinates. It will look like a piece of annulus. So this will be your footprint in R theta form. Okay. Again, I'm assuming that the footprint is a rectangle. Yeah. Now, next would be theta first. So you've already decided what angle it will be, and then theta would be RZ. So in that case, the footprint will be of the following form. So these are the different footprints we get depending on what we choose first. So the footprints are for the 2D region. Again, recall what we did was whenever we had a triple integral, we converted it into what? We converted it into integral over a double integral, right? So let's embark on first example here. Example 1. So find the volume of the solid that is enclosed by z equals to square root of x squared plus y squared and the sphere x squared plus y squared plus z squared equals to 2. So in this case, we will go essentially z first, right? So we'll go for z first. And let's look at the footprint. So footprint will be projection of this onto the xy plane. So this is the footprint. So footprint is a unit circle. So note when you're writing down the solution, you don't have to write down the whole thing, right? So you just have to basically write down these 4 steps when you're doing this problem. So now the question is, why is a footprint a unit circle? So let's work on that. So Z first, so footprint is unit circle. Why is that? So let's equate these together. So we need to find out the intersection of this cone and sphere and then project it down, right? So let's see, what is the intersection? So we have, take Z and equate it in this equation. So we have x squared plus y squared plus square root of x squared plus y squared. That is what Z is from the first equation, equals to 2. So this gives me x squared plus y squared times 2 is 2. So that means give me x squared plus y squared equals to 1. So footprint is a unit circle. Now, top and bottom. So what is the top? So the top is essentially the sphere. So what is the equation of that sphere? So for that, notice the following. We have R equals to so we have x equals to r cos theta, y equals to r sine theta. So this will become the top curve is top surface is x squared plus y squared plus z squared is 2, but x squared plus y squared is r squared, so r squared. So top is r squared plus z squared is equal to 2, which implies z equals to square root of 1 minus r squared. Now, why is that? 2 minus r squared. Since z is greater than 0, I'm greater than equal to 0, I'm only taking the positive root. Okay. Now, bottom is piece of this cone, right? So this is what the bottom is. Let's color it with a different color pen. So this is what the bottom is. So bottom is given by z equals to square root of x squared plus y squared, which is r. So therefore we get what? R is z is greater than equal to r, but less than equal to 2 minus r squared. Now, so I will draw the footprint. So footprint is a unit circle in xy plane, but we will take it as a polar coordinate, so it's r theta, right? So this is your top and bottom. Now what about sides? Now note that when you're talking about sides, excluding top and bottom, right? Exclude top and bottom surface. So, well, there is no sides excluding top and bottom, so there is none. So nothing to worry about there, or nothing to think about. Now for 2D plan, what do we have? We have, so in this case, we can write 2D, d equals to r theta, where theta is between 0 and 1, and sorry, r is between 0 and 1, theta is between 0 and 2 pi. So once we have this plan ready, now we are in a situation to write down the whole iterated integral, and which will give us the way to compute it. So let's write it down. So volume is going to be, so first goes z. So dz, z goes from 0 to 2 minus r squared. Then we go 0 to 1 for r, 0 to 2 pi for, so r d theta. All right. Now note that for the volume element, however, we need, for the volume element, we have r dr d theta. So there's this r, right? So we have to have that extra r here. Okay, so this whole thing is dv. Yeah. So now we have to compute the integration. So let's compute integration of dz. So this is going to be 0 to 2 pi, 0 to 1. dz integration is z. So r times, put z upper limit, which is 2 minus r squared. And we have dr d theta. Now we can do this computation. So here we can use substitution. So for the first integral, so you can break this integral to 0 to 2 pi d theta, 0 to 1 r square root of 2 minus r squared dr. So for the second integral, let 2 minus r squared be u. Then you will get 2r dr equals to du with a minus sign. Okay. So once you compute that integral, you will see, so this integral becomes, so first part becomes 2 pi, and the second part becomes 2 by 3 square root of 2 minus 1. So this is your integral. So yeah, so here we do the substitution, and then we can do the integral inside. All right, so as you saw, again, you just need to follow these steps and you are good to go with it. Okay. All right, now let's look at the next problem. So we have integral of x minus y dv, where E is the solid between the cylinders x squared plus y squared equals to 1, which is the solid, which is this cylinder, and x squared plus y squared, sorry, the outer one is x squared plus y squared equals to 16. The inside one is the inside cylinder, which goes vertically like that, is x squared plus y squared equals to 1. And then you're cutting it with a plane of this form. So you get essentially this region, all right? What region? The region which is, so let me remove all this now. So you get essentially the region which is bounded above by this blue thing, this blue curve, blue surface, my bad, which is annulus, cut in a slant way, of course it's not, and except the central part is not there. All right, so now we want to basically see what to do first. Again, as you can see that this is a region between, so this is again, Z can be seen as Z first region, so Z first. So your Z is between, so we need to see the projection, again, you need to see the projection of this solid onto XY or R theta plane. All right, okay, so in that case we have, so what is the footprint? So footprint is this annulus outside this small circle, but inside this big circle. So such an object is called annulus. So what is the 2D footprint of this? So 2D footprint is R goes from 1 to 4. Now bottom and top. So the reason why we decided to go for Z first, because we can write Z between two nice regions. So the top region is given by, well, so you have Z is between less than equal to y plus 4, but everything is terms of polar coordinates. So this will be Z is less than r sine theta plus 4. So this is the bottom surface, and this is the top surface. Now sides, so what are the sides? So in this case we have top here, we have bottom as that circle, and the sides, we have a side, right? So this is one side, and the other one is the inside one. So we have these sides as well. We have 4 faces. Out of those we have 2 sides. So 2 sides, so 4 faces, 4 faces, 2 sides. What are the sides? First side is the outermost cylinder, which is given by R equals to 4. The inside one is R equals to 1. R equals to 1. And these have no Z in them. Right? So check. So we can integrate that. Now for the footprint, we have again, for the footprint we have 2 circles. So footprint is this region here, right? And this region can be written in the form of, so 2D integration footprint region is 1 less than equal to r less than equal to 4, right? So r is 4 here, 1 here, and theta is of course the whole 0 to 2 pi. So then my integral becomes integral e of x minus y dv becomes the following. So first of all, we are going z first, and then we have r dr d theta, right? So the volume element is r dr d theta. So we again have volume element, and x minus y. So x minus y. So x is going to be r cos theta, y is going to be r sine theta. So r cos theta minus sine theta. Your range is for the first one, the range is from 0 to r sine theta plus 4. And then the next range can be for r 1 to 4. That's how we have written. And theta goes from 0 to 2 pi. Right. So now you can integrate it, but the idea is, the key is to be able to do this integral. You can certainly break this integral now and finish it off, right? Okay. So writing an iterated integral is the key part here, all right? Then the rest is usual computation. All right. Now let's look at the next example. Suppose we are asked to evaluate this integral square root of 2 to square. So your z goes from square root of x squared plus y squared to 2. Your y goes from this to this, and z goes from minus 2 to 2. And you want to evaluate this integral, right? So if you look at the, so if you want to look at it as a volume problem, this is how it looks like, really. Yeah. So your solid of integration is basically, so this is your solid of integration, right? Yeah. Sorry, you don't have this. If you did not have x square, y square, you were looking at solid. But since we have x square plus y square, we are not looking at the volume of solid, but we are integrating it over this solid region E. So how do we go about it? First of all, when you look at it, you can see the projection of it into xz plane, and that seems to be a circle, right? So again, we'll go Z first, draw the footprint, bottom and top, then look at the sides, and then have 2D integration of footprint, and then do the computation. All right, so let's embark on that. So first of all, if I have to write my E in terms of X, Y, Z, then it becomes what? It becomes minus 2 x less than equal to 2. Your y goes from square root of 4 minus x squared to 4 square root of 4 plus x squared. Not still 4 minus x squared, right? From minus of that to plus. And your z goes from square root of x squared plus y squared from this cone to this surface. So again, we are going for what? Z first. All right. Now, what is top and bottom here? So top is, so what is the footprint first of all? Footprint is, take z equals to 2. So how do you find out the footprint in this case? Take z equals to 2, you will get a when you cut it off, you get a disk, and project that disk down. You get what? Z equals to x squared plus y squared. So you get z equals to 2. That will give you that x squared plus y squared equals to what? 4. So therefore we get x squared plus y squared equals to less than equal to 4. So it's a circle of radius 2. Now what is top and bottom, and can they be written in terms of purely in terms of r and theta but no z? Let's see. So top is z equals to 2, and bottom surface is given by square root of x squared plus y squared, which is going to be square root of r squared, which is r because r is positive in this case. So we got the top and bottom. So your z is greater than equal to r but less than equal to 2. Now what are the sides? So you see that there's a top surface, there's a bottom surface, there's no sides, so no sides. So sides checked. Now what is the 2D integral plan? So 2D integral plan is, if you look at the D, region D, let's call this D, region D. D is going to be what? It's a disk. So it's basically r comma theta. R goes from 0 to 2. Theta goes from 0 to 2 pi. Then your integral, so we are evaluating this integral, right? So this integral becomes, let's call this integral I. So first we are going again z first. So z goes from r to 2. Then what about our r? R goes from, so r goes from 0 to 2. Theta goes from 0 to 2 pi. Volume element r dz dr d theta. I'm matching the order of integration with the limits of integration. So this is your volume element dv, and inside we have x squared plus y squared. So x squared plus y squared is r squared, right? So this will be r squared. And then if we have to integrate this, so this is a separable integral. You can basically write it as 0 to 2 pi. It's essentially integration over a rectangular box. So we have d theta, we have, not really, it's not integration rectangular box. We have to integrate 0 to 2 pi, 0 to 2, r to 2. This, because of this r, it's not a rectangular box, right? So we have r cube dz dr, and then we can compute this integral. It's going to be the first integral. This integral will become 2 pi. So this is 2 pi times. Now dz is going to be z, and when you put upper limit minus lower limit, it's going to be 2 minus r times r cube. Then we have dr 0 to 2. Okay. And a bit of a work would show that this is going to be 16 by 5. Okay, straightforward integration and then substitution. All right, so by mistake this has r, right? Okay. All right, so this is the process. Okay, now let's look at another example. So in this example, we are given a solid lies within a cylinder, x squared plus y squared equals to 1. So this is your cylinder, x squared plus y squared equals to 1. Okay. And below the plane z equals to 4. So z equals to 4 will basically cut it in just like that. And above the paraboloid, z equals to 1 minus x squared minus y squared. So that paraboloid is over here. Yeah. So that is the paraboloid. So you are above this paraboloid and below this, so parts here. Okay. So let me just erase that now. The idea is clear. The density at any point is proportional to the distance from the axis of the cylinder. Find the mass of E. I see. So now in this case, we are asking about a mass of the function. So we need to know what is the density function. So what is the density function in this case? So in this case, what we have is rho is the density function rho of x, y, z is proportional. That means it's some k times distance from the axis of the cylinder. So this is the axis of the cylinder. You take any point, its distance from the axis of cylinder is essentially square root of x squared plus y squared, right? So this is going to be square root of x squared plus y squared. Now we want to basically, so if you write down this solid in terms of x, y, z, then it's essentially z is bounded between the solid above and below, and then the bottom where you're integrating is a disk, right? So let's embark on trying to write this in terms of polar coordinates. Again, in this case, we have z is changing between 4 and 1 minus x squared minus y squared. That is 1 minus r squared, right? So this is your top and bottom. So let's just write that down. I'm going to write that down here. So z is changing from 4 to 1. 4 is on the top, right? So it's top is z equals to 4, bottom is 1 minus r squared. So this is 4, this is 1 minus r squared. And your footprint is, the footprint is projection D is a unit. So if you look at the projection, you will look at it, you get 1 minus x squared minus y squared. So you are at cylinder, right? So x squared plus y squared equals to 1. So we'll have x squared plus y squared equals to 1 is a unit circle. Again, all right. So now what we have is, so now we want to basically, so we got top and bottom, this is a unit circle. What are the sides? So the sides are essentially, how many sides are there? So there's top and bottom, but there's this one side. This is the side, right? So the side is essentially, side is a cylinder, x squared plus y squared equals to 1. That is r squared equals to 1. That is r equals to 1 because, so it is independent of z. Okay, so one side other than top and bottom, top and bottom. So now what is the 2D integration plan for the footprint? Is going to be 2D integration plan is going to be again, it's a circle, so theta goes from 0, so r theta, where theta goes from 0 to 2 pi, so 0 to 2 pi, and r goes from 0 to 1. So what if I have to write this solid E? So now I can write this as rho as my function as square root of kr, right? And what if I have to write my solid E in terms of spherical coordinate? So how will it look like? Sorry, in terms of cylindrical coordinates, how will my E look like? So note that E will then look like r theta z, right? Where theta goes from 0 to 2 pi, r goes from 0 to 1, and z goes from 4 to 1 minus r squared. Yeah. So same thing we should have done here as well. If you're interested, we should basically look at E we have done here in polar. So we should write E in polar, sorry, E in cylindrical. I'm using a subscript to indicate that we have cylindrical r theta z, where your z was between r and 2. Again, your theta was between 0 and 2 pi, and your r was between 0 and 2. Now, same thing here as well. What is your E in this region? So let's write that down as well. So what would be my E in this case? So E was, again, r theta z. Now, the projection was an annulus. So Z was between, so Z was between r sine theta plus 4. I'm writing it down there because I don't have space here. My theta went from 0 to 2 pi, and your r went from 1 to 4. Yeah. All right. So this is how we wrote down the solid. Again, in this case, let's write down the solid E. So what did we get? We got the solid E to be, again, E in cylindrical. So I'm just writing the subscript so that it's clear. You don't need to write that though. R theta z, where r is between, so z is between r and square root of 2 minus r square. Then r was between, well, then the bottom was a circle, so r was between 0 and 1, and theta was between 0 and 2 pi. All right. Now let's move on to the next problem. Okay. Now in this case, again, so find the volume of the solid T in the first octant that is bounded by the cylinder x squared plus y squared equals to 2y, and half cone z equals to square root of x squared y squared and the yz plane. So again, we'll have to look at the, so again, this is what z first region. However, did we compute we did not finish this, right? So let's write this, first finish this problem. So in this case, we have mass is going to be E integration over E K times R dr d theta. So we need z first. So r dz dr d theta, which is going to be again 1 minus r square in the bottom to 4, that is, and then here we have the density function is kr. Then let's integrate in terms of r. So dr is going to be from 0 to 1. So this is dz dr, and theta is going to be from 0 to 2 pi, right? And then once you do this computation, you can see that this is going to be k common 0 to 2 pi of d theta. You have 0 to 1, 1 minus r square, 4 to r dz dr d theta. And when you simplify this, you will get this is equal to k times 2 pi integration 0 to 1 of dz is z. So we have 4 minus 1 plus r square, and then we have dr. D theta was already used there, right? Okay. And then when you integrate this, so this is going to be k times 2 pi. This is 3 plus r square, so that's going to be 3 plus, sorry, there was an r. K is proportional to distance, so we get r, so there is an r square right here. So we had r here, so that basically makes it r square. So this will be r square. This will be multiplied by r square. That will be 3 plus r square times r square. So that's going to be 0 to 1, 3 plus r square times. So we get 3r square plus r to the power 4 dr. That is going to be 2 pi k, and you integrate, this is going to be r cubed plus r to the 5 over 5, 0 to 1, and then the answer is 12 pi k by 5. Okay. All right, so let's move on to the next problem now. Again, this is a Z first region. All right, so seems like we have done many Z first region. We should try theta first or R first region as well, okay? That you can see in the live class. We'll do one problem on that. So again, here we have Z first region. What is a footprint? So if you project it down, you get a footprint here. Let's evaluate that footprint. That the footprint is essentially, you can see that this is x square plus y minus 1 square equals to 1. So it is a circle x square plus y minus 1 square equals to 1. And if you write it in polar coordinates, sorry, cylindrical coordinates, now we are, see, that's the thing, right? So cylindrical is basically polar plus vertical, right? So in that case, we have, so footprint is a circle. We'll come to that. Now, what is top and bottom? So top is given by z equals to square root of x square plus y square. That is same as z equals to r. This is top. Bottom is, well, bottom is the cylinder, which is, so bottom is this circle here, right? because we are also saying the xy plane. So the bound is by xy plane. That is given by r square. Put in this equation, take x equals to r square equals to 2 r sine theta, which implies r equals to sine 2 sine theta. Now, what are the sides? So side is basically a cylinder x, the same cylinder, r equals to, so we get the side is the same cylinder. So side is this circle actually, right? So we get, so side is this circle, again given by the same equation. We have r equals to 2 sine theta, does not depends on z. Okay. So now what is the 2D plan for integration? So d can be written as r theta. And if you see this, your r goes from, so your r goes from 0 to 2 sine theta, whereas your theta goes from 0 minus pi to pi, right? Minus pi to pi. Sorry, 0 to pi, my bad, right? You're starting here, your angle starts here and goes all the way down there, right? So 0 to pi. And in that case, the integral can be written as, so we are finding the volume, so V can be written as, again, the first is going to be Z, which goes from Z equals to 0 to top one, which is Z equals to, what is the equation of that? Is Z equals to R. And so I should have written that here. So here, Z is greater than 0, less than equal to R. Or R goes from 0 to 2 sine theta, and theta goes from 0 to pi. Now we need to write down the volume element, which is dV, which is R, dz, dr, d theta. So yeah, so in that case, we can basically see that this is going to be, so dz, when you integrate, you get r, z, and then when you put the limits, you get r square, 0 to sine theta, and we get 0 to pi, dr, d theta. So this is going to be 0 to pi, r cubed by 3, and r cubed by 3 is, when you put the limits, you get 8 sine cube theta by 3 d theta. And then you can do the usual conversion. You can basically leave one of them, say 8 by 3 outside. You can write it as 1 minus cos square theta times sine theta d theta, and then do the conversion. All right, it's u sub, right? So sub cos theta equals to u, and that will solve your problem. So these are the techniques we have in the cylindrical setup. Now let's do the same problem. So recall this problem. So we will do the same problem. Until now we have done Z first mostly. So let's for a change, do this problem in terms of theta first. Okay, so how would we go about it? So now we want to do the same problem. Say we want to do this problem in terms of theta first. Theta first. Okay, so first step again is to ask about footprint. So what is the footprint of this? So let's expand this out. What is the footprint? So let me erase this so that we can see the footprint. So footprint in theta would be and there we can see that it's essentially a triangle. So in this case, it's basically a triangle, right? So this is our D. So what is the footprint? So footprint is basically going to be a triangle. Now, what is, so this is a triangle, it's a triangle D, so footprint is, so 1. Now let's go through all the steps by ourselves. 1A, footprint is a triangle. Now, what is bottom and top for theta? Well, bottom and top for theta. So theta is pretty straightforward, 0 to theta is goes from 0 all the way to 2 pi. So top and bottom, theta goes from 0 to 2 pi. Now, then sides, what are the sides in this case? The sides are, in this case, in case of theta, the sides are z equals to 2. So let me draw with a different color pen. So sides are z equals to 2 and z equals to r. So we get sides are two sides, so two surfaces, z equals to 2 and z equals to 1 minus r. They don't have no theta in them. Perfect. So basically you can think of this region E is a cylinder in theta direction. All right. Now, so once now what about